Welcome to another podcast. In this episode, we're going to be taking a look at our first glimpse of what are called transforms this semester. This is a topic which appears in both the ordinary differential equations course as well as in the partial differential equations course. In this course, we focus primarily on what's called the Laplace transform, but before I jump too far into the details of that transform, I want to give you a basic overview of what a transform is. And I think the best way to do this is sort of this idea of a black box sort of system where you've got some sort of operation that occurs here where you've got a function f of t and you pass that function into the box. The box is the transform, and out pops this sort of new entity that's a different function altogether of a different variable. So this is transforming the variable t into the variable s. And so the transform is just this mysterious thing that takes a function in one domain and associates it with the function in another domain. Compare this, if you will, to something like an operator. And operators we're really familiar with. Examples of operators are things like the derivative and the integral and so on. These take t and keep it in terms of t. So if you've got a function f of t that you try to pass through an operator, then the result is a different function of t. For example, if you operated on the function e to the 3t, then it passes through the operator. So the operator here is d dt. It passes through the operator and out pops the function 3e to the 3t. The point is, we didn't change the domain. So we're very familiar with how operators work. We're less familiar with how transforms work. And I think it's because we don't have all that many good examples of transforms that are apparent. You've actually used a transform before, whether you realized it or not. So I want to give you an example of it. And the best example I can come up with is a power series. Power series are transforms. Let's see why. If you think about your basic power series, you've got a infinite sum. Let's say the sum n goes from 0 to infinity of a n x to the n. And, that's the polynomial a0 plus a1x plus a2x squared and so on. And we know that power series can be associated with functions. So let's say that this is equal to some function a of x. Then let's think of it in sort of the black box terms here. In order to define the function a of x, you have to first define the coefficients. So if you give me a coefficient, I can give you the function a of x that corresponds to it. For example, let's suppose we used the function a of n equal to 1. Then you know that if you plug 1 in for the coefficients, then that leads to the sum 1 over 1 minus x. And this is only valid for the absolute value of x less than 1 because this is the geometric series when all the coefficients are 1. Similarly, if my coefficients a n were 1 over n factorial, then I associate that with the power series 1 over n factorial x to the n, but that's just the exponential e to the x. And so what you should be looking at here is the power series transforms a variable of n, so this is dependent on n, into a variable of x, where the domain switches. And so power series are a great example of a transform, and it turns out that when you want to talk about Laplace transforms or Fourier transforms, as we'll talk about in PDEs, they are really just the continuous analog of the power series. So for example, the idea here is if you look at the an that we have here, then I have my power series, and this is valid for values of n equal to 0, 1, 2, and so on. But if I'm wanting to think of this continuously, then I should have a continuous variable. I would replace the integral, I would replace the sum with an integral, I would be looking at a as a function of a continuous variable, we'll call it t, and x is also raised to the continuous variable t. And this is where t ranges from, well, some value here. The most appropriate value is if n is going to go from 0 to infinity, then t should also go from 0 to infinity, which means the limits of integration would be 0 to infinity in this case. Now, while that's all well and good, it's still not all that convenient of a notation for us, particularly because if this thing has any hope to converge, it's an improper integral. If it has any hope to converge, then x in this particular problem, x must be less than 1. And we typically don't want to use bases that are power functions. We would much rather have the base be the exponential e as opposed to being x. And so the idea there is I can take x to the t and rewrite it. This is just a sort of a cosmetic improvement here. I can write it as e to the natural log of x raised to the t. That's the same thing. And what I have here at this point is e to the natural log of x being less than 1, but that's only true if the natural log of x is, in this case, less than 0. You can see here that if I make that change, then I'm looking at natural log of x instead, and that natural log of x would be less than 0 in that case. So I'm going to have natural log of x as a negative value. So I might as well just replace the natural log of x with a negative value. I'm going to call it negative s to the t, or e to the minus st. Now this is all purely cosmetic. We're just doing a change of variables here, and the result is that we have transformed the power series into this integral from 0 to infinity of, we've got some function a of t here, which was previously coefficients for the power series, but we're going to think of them as functions here. And then we've transformed x to the t into e to the natural log of x to the t, and we've made a simple change of variables here by replacing natural log of x with negative s. So once we make that change of variables, this becomes e to the negative st dt. And it turns out that this is what is known as the Laplace transform. And what I want you to get out of this mainly is that the Laplace transform is the continuous analog of the power series. Now there's a little bit of notation that we need to go over here. The first bit of notation is the way it works is the transform is this script L. That's the Laplace transform. I don't want to call it an operator because it's not an operator, it's transform, but L is the notation for the transform. So what we say is that when the transform acts, it acts on functions in the t domain, in the continuous domain, and its output is a function of a completely different variable, in this case s. You can see that when I integrate out t, s will be the variable which remains. And so this is the frequency domain, or excuse me, this is the time domain, t is. So you take problems from the time domain, and it turns out that what ends up happening is you switch to the frequency domain when you do a transform. So you associate with the function f of t the function which looks at its frequency in the frequency domain. The best way to go about doing this and sort of understanding what the transform is by actually finding the transforms of particular functions and seeing what happens. We're going to do that in future videos. But there is one more property I want to make sure you're aware of. Just like all the operators we use this semester, like the integral and the derivative, this is what's called a linear transform. And what it means for the transform to be linear is that if I take the Laplace transform of a function alpha times f of t plus, say, a beta times g of t, Because the transform is based off the integral, and because the integral is linear, the transform will also be linear. This means that this is the same thing as taking, if I think of L as being the integral, we all know that you can do scalars, which that's what alpha and beta are here. Alpha and beta are scalars. You can take scalars and move them outside the integral. I can take scalars and move them outside the transform. The transform only acts on things in the time domain, not the scalars. So the Laplace transform then, this would be of f of t plus beta, the Laplace transform of g of t, and our convention is that we will replace the Laplace transform of the lowercase with the uppercase, kind of like if you're doing an antiderivative. And so this would be the notation that we would use, uppercase f and uppercase g, to denote that we've taken the Laplace transforms of those. The reason you know that those aren't antiderivatives, by the way, is because you switched the variable. We started with the variable in terms of t, now we're looking at the variable in terms of s, which is the frequency variable associated with the function of t back in the time domain. Right, in the future videos, we're going to take a look at various functions f and their associated Laplace transforms, capital F. And so you're going to want to pay close attention to that, and we're going to kind of build a library of different Laplace transforms and their associated functions. All right, thank you for watching.